Well, I guess first off, you're Chris. How do you say your last name?
Yeah, Chris Colose.
Colose.
Yeah.
Okay. And what do you work for NASA Goddard?
Yeah, so there's a small institute in uptown Manhattan that does it's primarily an Earth climate modeling center. There's a small group of people that do kind of the official, when you hear 2020 warmest year on record or something, that is one of the main groups in the world that is producing those products for temperature, global temperature estimates and so on. I don't work on that, but that is done there. But it's primarily a climate modeling center, mostly geared toward Earth climate modeling. But there's a few people that have kind of done modeling of planetary atmospheres and exoplanet interests and such. But it's mostly a climate science focused institute. I work from home now with COVID and everything, but normally I'd be in Manhattan. So I'm relatively early career. I did my PhD in 2000. What year did I finish? 2015 or something. I forgot. But I did a couple of years of a postdoc, and then so I'm a couple of years removed from that. So still kind of young, but
fresh.
Yeah, I've taken an interest in kind of, back when I guess blogs were, I think the era of science communication has changed a little bit, but I'd say in the 2000s, early 2010s, when blogs were a big thing and such, I did a lot of that for climate change interests. Here's how things work and just getting that. And now people use a lot of Twitter and so forth. And so I kind of participate in that when I can, but that's me. And now I do, now my research is mostly, so I'm kind of part of that exoplanet modeling group at GIS. And I've mostly, my recent stuff has primarily been in the effect of various orbital configurations on climate. So I've done things on, simulating Earth or other planets at different obliquities, different tilts, different seasonalities. I've done different eccentricities or orbital configurations, spin orbit resonances, and so forth that planets can find themselves in, subjected to tidal forces and so on, and how that influences climate. So that's primarily what I've done recently.
Okay, so you're more theoretical.
Yeah, I would say more theoretical. I guess climate modeling's, just philosophically in a weird, boundary in the experimental and categories of science. It's not observational, but it's kind of when you take 1 million lines of Fortran code and do experiments with that, I'm not quite sure what to call it, but that's kind of the domain we wrestle and then try to make contact with real world observations where they're possible. A lot of it is inherently theoretical because you're talking about, we're going to model some exoplanet that we don't even know exists. And so, it's kind of strange, but yeah.
But I mean, in a vast universe, it probably exists somewhere, right?
Right. Yeah. It's we'll just, for example, a simple, thing is let's just model an aquaplanet, just an ocean covered planet, because that's sort of a simple, starting thing. You don't have to worry about continents and stuff because you don't know what continents look like on other planets if they even exist. So let's do an aquaplanet and see what behavior emerges on it. And then you publish that as a result and say, well, if you do this to that, aquaplanet, then this happens. And you expect those results to kind of carry over to more, complex configurations. But it's hard to test a lot of these things. So,
right.
Yeah.
Okay. So I was Well, I was, like I said, I was in the email. I was reading about you online, and looked up some of, the papers your name is on, and then I stumbled across this question that you asked at a conference, which was basically, what if Mars and Venus switch places? And you wanted to sort of start a discussion about what that would do to, say, their atmospheres, for example.
Right. Yeah. So when I initially posed it, well, I guess there were sort of two questions that emerged, and end up at the conference. We ended up getting probably 25 or 30 people together to talk about this, and it was great because they all had backgrounds in different things, geology or astrophysics or climate, and so everyone had kind of something to say about it. But I was kind of interested in two questions. One is what would happen if you did it now, if you just did a little swap. And I don't have much to say about the orbital, stability of that. I'm just assuming you can do that, and
Right.
then that they would just be happy in that configuration. But if you did that now, what would happen? And then my initial motivation, though, was actually if you did that, 4 billion years ago, how would the two planets have evolved differently? And could you, for example, have two habitable planets now instead of one, which is Earth? But so we can kind of run through both of those questions. And yeah, so I guess where to begin here.
So I guess let's just start with what happens if we take Mars now and we put it in Venus's orbit.
Right. Yeah. So Mars now is it's a small planet. It has a very thin atmosphere. It's like 6 millibars of surface pressure. Earth's about 1,000 millibars, so it's very thin atmosphere. It's pretty cold, of course, being at the Martian orbit. Although because there's not a lot of heat transport, there's no oceans, there's a very thin atmosphere. You get big day to night temperature gradients, pole to equator temperature gradients. So it actually does get above freezing at, say, noon at the equator on Mars. Although liquid water is not stable at that pressure, but it does get above the freezing point. But
right. So just to clarify, right, like even though it can get above freezing, the reason that liquid water isn't possible is because it's below what we call the triple point, right? The pressure is way too low.
Right. Yeah. It wouldn't be thermodynamically stable at the modern Mars's pressure. Although we'll get into in the ancient past, there's geologic evidence on Mars for ancient water. So you would infer that the atmosphere was thicker in the distant past. But we can get into that in a little bit. But yeah. So I think Mars moving to Venus's orbit. My expectation is actually that not a whole lot would change. It would get a little bit warmer. So if you just work out the math of how the temperature of a rock changes as you go to Venus, to Earth, to Mars, it's kind of an inverse square root dependence. So it's not, it's there, but it's not that strong. Venus, if it didn't have an atmosphere, if it was just a rock, would be, maybe a little bit hotter than Earth's tropics. It'd be hotter, but not, it wouldn't be hot enough to melt lead if you just account for the distance to the sun. But so Mars would be warmer, and then some people who have done estimate, I think in some of the articles that you might have found on that topic, people were pointing out that you would melt some of the ice caps, and on Mars there is both water ice and carbon dioxide ice, because CO2 gets cold enough to condense at Martian temperatures. But so you would release a little bit of that CO2, so you could kind of generate a little bit more of an atmosphere through that process, but it's not a lot. So so my expectations, it would just be a little bit warmer of a rock. And I don't, it's kind of hard to say all the intricate things that would occur, but it's still, the modern Mars, it's still a very thin atmosphere. And so it's hard to be too. I don't know how excited I would be about a little bit warmer of a thin atmosphere of Mars, but
So would the atmosphere be even thinner because the solar wind is stronger there, or?
right. So so atmospheric escape is another interesting topic, and it's a little bit outside my wheelhouse, I should say. But I've been told that you should expect that right now Mars loses some atmosphere just from erosion from the solar wind, and you would expect that process to be a little bit faster as you move inward. Um, but again, right now in the in the present day, you know, Mars is almost an airless body, not quite, but it's almost there. And so it would be, yeah, it's difficult if you really. I don't know exactly how the atmospheric pressure would change. If you released a little bit more CO2 into the atmosphere that's frozen up, and then you strip away a little bit more atmosphere from escape, what the sort of equilibrium would be. But it's pretty much now a nearly airless body, and that's and it's tectonically dead.
Right. So short answer, it's complicated.
Right. Yeah. Now Venus, if you did the other problem, Venus to Mars. So Venus right now is in a lot of ways a lot more interesting. In my opinion, it's a lot more interesting than Mars, but a lot of people disagree. So, but it's a very thick atmosphere, so it's kind of the opposite end member. It's almost 100 times the pressure of Earth's atmosphere, and it's almost all CO2. And because of that, that's why it's so it's over 700 Kelvin the temperature, and it's the hottest planet in the solar system. And also because of that thick atmosphere, there's essentially no horizontal temperature gradients between day and night. Even though it rotates very slow, there's still almost no day, night, or pole to equator temperature gradient.
So it allows the thick atmosphere allows the temperature to sort of like conduct around the planet.
Yeah, I would say conducts probably not. I mean, essentially, you just have a lot of heat transport by a fluid envelope, and also when you have a slow rotator, the equations of fluid dynamics don't allow for big temperature gradients to develop on slow rotating bodies. But yeah, even if it rotated faster, with a very thick atmosphere, just because of how with a longer time scale for radiation to, for example, for the planet to lose radiation as an energy source to space, it would you wouldn't get big temperature gradients. So you're essentially comparing a radiative and a sort of dynamic time scale, but you wouldn't get big temperature gradients. But but on Venus, it's very hot now. The thing with Venus now, though, is that very little sunlight actually reaches the surface. So it's already, even though it's closer to the sun, it actually absorbs less sunlight than Earth. Because it's very reflective, and there's two reasons for that. One is it has sulfuric acid clouds, which that's another kind of part of Venus's. It's chemically interesting, but Venus has sulfuric acid clouds which are very bright, and so. If you're, I mentioned if you have a rock at the Venus sun distance, it would be like Earth's tropics in temperature, but actually, I guess a better comparison would be to make a bright rock with a high albedo, and then it would actually be colder than a rock at Earth's distance that was Earth's reflectivity. so Venus already, and then the other reason, there's just, even without the clouds, because Venus has a very dense atmosphere, there's actually a lot of Rayleigh scattering, and CO2 is a better Rayleigh scatterer than a nitrogen oxygen mixture, and so Venus would still be pretty reflective even without the clouds. So the bottom line, the point I'm making is Venus just doesn't absorb a lot of sunlight, and a lot of the sunlight doesn't reach the surface. Only a trickle of sunlight reaches the surface. And so if you decrease that even further, it's not really clear that. So if you move Venus to Mars, it's not immediately clear that that would make much difference either, because Venus now it's kept warm by it's a trickle of sunlight, but the heat just can't escape because of its greenhouse effect. It's kept warm by essentially, you put 1,000 blankets over you.
Right. So it's basically too late for Venus at this point.
Right. Yeah. So Venus can't. Yeah, it doesn't lose energy very efficiently.
But I mean, at this point, right? If we moved Venus now to Mars's orbit, could we still like live in cloud cities?
Well, I guess, I mean, at some point, even Venus and Venus's orbit is, at some point, temperature decreases with altitude.
Okay.
Pretty much any planet. So that's just the way that's basically anytime, unless you have something like ozone that absorbs radiation up in the atmosphere, temperatures always decrease with height, just like if you're going up in a mountain or something.
Okay.
So right now, there is some layer, in Venus's cloud decks that has Earth-like temperatures. And that's when I don't have a whole lot to say on like the phosphine story, but when that was popular a few months ago, that was kind of there was some layer that was near Earth temperatures and Earth pressures, in fact, that people were interested in for whatever that detection signal was. Right. Probably not phosphine, but yeah. So that's true now in Venus. Okay. If you moved it to Mars, though, it's not clear, because you still have the fact that you're just not getting a lot of sunlight, even though it's reduced a little bit. But I'm not sure a lot would change. Now, if you eventually flung Venus out and just made it a rogue planet, eventually it would cool down, of course. But it's not clear what that time scale would be. It would take a while for Venus to cool down, just because it has such a thick atmosphere. But eventually,
if it's not receiving any light or any energy from the outside, it's going to have to cool down.
Yeah, eventually it's going to have to cool down just to come to equilibrium. It would take a little while, but. Because then you're just heated by any, if any, just geothermal heating or something, which is very small. But eventually it would cool down. But I think at Mars, it's still getting enough sunlight. So I actually wouldn't expect a whole lot to change on Venus. But it's an interesting problem that I'm not sure anybody could answer right now. Climate models aren't really suited for what happened for Venus right now, with a super thick atmosphere and its chemical, all the chemistry that happens on Venus. We don't really model Venus that well, but
we'd probably need more data, right? We need to actually like go there and stay there for a while.
Yeah, going to Venus would be nice. It's been a while since we've actually had a probe in Venus, but of course. Yeah, I mean, the hypothetical question we're asking, there is no data for it, of course, but
right.
But yeah, I mean, but to actually model that scenario would be interesting. I'm not sure any group has a climate model that would be well suited for this question at the moment. So I am speculating, but yeah. So I guess in both cases, swapping Earth and Venus now. It's almost boring in that I'm not sure a whole lot would change. I think Mars, would be a warmer rock, and Venus would still be probably an inferno. But
so before we get into the second question, though, where we say, well, what if they formed in the respective locations? Let's just talk about the greenhouse effect for a couple minutes. Mm-hmm. So. I mean, my understanding, right? There's a difference between the greenhouse effect and like a runaway greenhouse effect.
Right.
right? Like it's okay in moderation, and we have that a little bit on Earth, right?
Right.
So what exactly causes that?
Just the greenhouse effect you're talking
Yeah, so
about?
like there's greenhouse gases, right? So like what exactly is a greenhouse gas?
Right. Yes. So a greenhouse gas is anything that, well, essentially any gas that absorbs planet radiation or infrared radiation, which any planet that's kind of not, several thousand degrees Kelvin is emitting primarily at infrared wavelengths and longer wavelengths than the star. And so I mean, you can have gases that absorb solar radiation as well, but a lot of the gases we're interested in these discussions, carbon dioxide, for example, absorbs very well at certain infrared wavelengths. And essentially, so for a given surface temperature, it makes it adding a gas that absorbs infrared radiation makes it more difficult for a planet to lose energy to space, and that is the only way planets lose energy to space is through infrared radiation. You can't conduct heat out into a vacuum, you can't convect out into a vacuum, so that's how planets lose energy. So the basic energy balance of a planet is well, at least for all the planets in well, the rocky planets, Earth, Venus, Mars, it's a balance between absorbed solar radiation from the star and then outward infrared radiation that's emitted by the planet. You can have other heat sources, tidal heating or so forth, but that's not relevant on Earth. Or geothermal heating, which is very small on Earth. But and so you're essentially trying to find a temperature in which the absorbed solar radiation and the outgoing radiation can balance, and it's because the outgoing radiation is a function of temperature, and so that allows an equilibrium to be found. Okay, so the greenhouse gas is essentially, I mentioned that temperature decreases with height in any atmosphere, and actually what another way to look at it is that when you increase the infrared opacity of an atmosphere, if you're just tracking an infrared photon, the statistics of where those photons are sort of leaving the space is occurring higher and higher up in the atmosphere as you make it more and more opaque. So right now an infrared photon doesn't have it can't really go from the surface immediately out to space very efficiently, and if you keep adding greenhouse gases, then that's even more true. And so you would have to look, if you were sort of looking down at the planet with infrared goggles, you would see photons emitted primarily from many kilometers up in the atmosphere. You
wouldn't be able to see the surface,
right? In some way, and again, it's wavelength dependent, but if I'm just considering like a bulk infrared average of the spectrum, then it's the mean photons being emitted many kilometers up in the atmosphere. And on Venus, it's if you looked at Venus in the infrared, it looks colder than Mars because all the photons are being emitted from very, very high up in the atmosphere, because that's when it becomes optically thin enough for those photons to escape. But because temperature decreases with height, and you add opacity, and those photons are now being emitted at a colder temperature. Now there's an imbalance. Right now there's absorbed solar radiation coming in at a higher rate than energy is being lost to space, and so. So then the way the planet comes to equilibrium is by increasing its temperature. And so the way you get the outgoing radiation to balance is it's a tug of war essentially between temperature and the infrared opacity. If you increase the opacity, then it makes it harder for photons to get out, and so then you have to increase the temperature to make it more emissive essentially. And then if you decrease the opacity, then then the planet will cool down.
And so on Venus, it's just out of control, right? There's so much greenhouse gas in the atmosphere that the heat is just held, the infrared light is just held in.
Yeah. And so you would have to get up very high in the atmosphere before sort of your average photon can escape to space, and that's occurring at a very cold temperature. But it's very high up. If it's sort of like, I mentioned that temperatures decrease with height, so you can imagine a curve that has some slope that's temperature versus height, right? And so
right.
It's warm at the surface and cold up in the upper atmosphere, and that slope is essentially set by convection. It doesn't really change much when you add greenhouse gases, but it changes the intercept of that curve. So the whole profile shifts to warmer temperatures, and so if you increase the average height at which a photon is allowed to escape to space, then the whole profile has to shift so that you're essentially the emission level is at a higher altitude, and then the whole profile is shifted to a warmer temperature, including at the surface, but at any point along sort of the adiabat, the temperature profile. And Venus, so Venus is, as I mentioned, it's just getting a trickle of sunlight, and but it can't lose energy by infrared radiation very efficiently. So it actually it has to convect very, very much higher than in Earth's atmosphere. That's the only way you can transport heat vertically in Venus until you get to very, very, very high in the atmosphere. It's just a convective layer until it gets very high. And then finally, when you get to like the very top of the atmosphere, then you can lose energy at a rate that balances the absorbed sunlight.
So are you telling me that Venus's atmosphere has convection currents in it?
Yeah, I mean, it's all what we call a troposphere on Earth is essentially that's defined by a convecting layer, and Venus is almost all a troposphere. Earth's almost all a troposphere too. Eventually, you get into a stratosphere where you have ozone absorption and temperatures actually increase with height, but it's not a very big fraction of the mass of the atmosphere, but yeah, on Venus, it's convecting. Essentially, any planet is convecting. I mean, you can think of exceptions, but if somehow you can have a almost uniform temperature with altitude, it's a stable temperature profile, but you need some other process to keep it in that configuration. But yeah, typically the, I guess, default state of a planetary atmosphere is one in which it's heated by sunlight and it's convecting upward, and then energy is being emitted to space through infrared radiation at some altitude.
Okay, so the warmer atmosphere at the surface rises up due to buoyant force or whatever you want to call it, and then it cools off in the upper atmosphere and then falls back down.
So if you're just talking about air, then mass has to be conserved. I mean, there's circulations in which air, and that's weather, right? If air is rising somewhere, you get clouds, but it has to be sinking somewhere else. But just from an energy balance standpoint, if I'm thinking about how do you create a planet that has some equilibrium temperature that it's happy to be in, then I guess the conceptual picture to have in mind is one in which again, so the Earth's absorbing some amount of sunlight. For Earth, that number is about 240 watts per square meter. So it's just an average kind of over the sphere of the Earth. And so the planet needs to emit 240 watts per square meter out, and it does that in the form of infrared radiation. But again, that radiation is, sort of the bulk of it is coming not from the surface, but from some height in the atmosphere. And but beneath some layer where it's easy for infrared radiation to escape, then there's going to be convection that's occurring, and that convection will essentially create a temperature gradient that is dynamically stable. That's called the adiabatic lapse rate. It's and it can have different slopes depending on things like if water is condensing or not, because that is a heat and that provides heat. But for Earth, it's something like 6 to 10 Kelvin per kilometer, the slope of that temperature gradient. And so that's a dynamically happy temperature gradient. If it's steeper than that, then convection just wipes away that instability. But eventually it's going to get optically thin enough for photons to escape to space. And so I think to your question on Venus, it's the greenhouse effect, which you could call it a supercharged greenhouse effect. The term runaway greenhouse effect, I'll mention in a moment. It's kind of reserved for something different than just a very strong greenhouse effect.
Okay, so this is why I've never done a video on this, because I'm going to slip up and say something like that in the wrong context.
Yeah. So actually, Venus is not in a runaway greenhouse effect. You can. It's fair to call it strong or supercharged or whatever.
But it's reached an equilibrium. It's done.
Right.
Okay.
Right. It's an equilibrium, and it's just a very hot equilibrium. It's because the greenhouse effect is so strong. There's just so much CO2 in the atmosphere. Essentially, as I mentioned, that radiation has to come from a very, very high altitude to escape into space, and so it just has to be very hot in order for the whole planet to lose as much as it needs to do. So the term runaway greenhouse refers to a very specific process in which I should draw a schematic or something at some point. It actually refers to a very specific process in which the outgoing radiation cannot reach what the absorbed solar radiation is, and it turns out that there are limits to how efficiently an atmosphere can lose energy to space when you have water vapor in the atmosphere, as well as other things. But water vapor is the one we're interested in for Earth or Venus, because that's the condensing substance that is of most interest. And so what happens on Venus, what is thought to maybe have occurred on early Venus, but more generally the runaway greenhouse process in general, which can occur on some exoplanet as well, is that when you make the planet hotter by some means, you get a little bit more water vapor in the atmosphere. It's sort of a positive feedback, and water vapor itself is a greenhouse gas. That's what makes it a positive feedback. So, and this is relevant in the climate change context as well on Earth, is we think that when we double carbon dioxide, for example, the atmosphere will become a little bit more moist. It can sort of it's just a thermodynamics problem. It can sort of theoretically hold something like 7% more water for every Kelvin that you make the planet hotter. And so that does amplify the greenhouse warming by a factor of 2 or so. So if you ask the question, how much does CO2 warm the planet when you double? there's the direct effect of CO2, which is about a degree or so, and then there's these feedbacks which you need to include to close the problem. And the biggest one is water vapor. The fact that you have more water vapor in the atmosphere makes that like 2 degrees. And then there's some other things.
So if there's more water vapor in the atmosphere, say on Earth, does that mean that more water is just evaporating, or does that mean there's less rain?
Oh, that's a great question. Yeah. So you don't need, so you don't actually need more evaporation. It's often quoted that, the reason you have more water vapor is because there's more evaporation. And it tends to be that you do get more evaporation in a warmer climate, but it's not necessary. You can imagine situations in which like the wind speed at the surface goes down or something, and so there's less evaporation, but you'll still end up with a more moist atmosphere, just because it's just a Clausius-Clapeyron thermodynamics. If you take a substance, and it has some equilibrium of liquid and ice and vapor, and you shift it to hotter temperatures, it wants to be more in the vapor form. And so essentially the atmosphere can just hold more water vapor. It's kind of, fluxes versus reservoirs issue when people talk about evaporation. But as to rainfall, and I should say some people don't like the term hold more water vapor because the atmosphere is not a sponge. It's like, you don't need the other molecules for that to be true. It's just, water is more preferentially in the vapor form, and it's happy to, you just can't, if you get too cold, the vapor just condenses and you get clouds and rain. But as you shift things to hotter temperatures, you're able to just have more water vapor, and so we do think, in the future, Earth will be, it'll be a more moist atmosphere. The rainfall question is actually interesting because the rainfall is not vapor limited generally. It's more energetically limited, and so when you look at projections of, say, the amount of water vapor in the atmosphere versus the amount of rainfall that occurs in the future, those things don't scale with each other very well. And so there's other mechanisms at play on how fast, the sort of the average part of a planet can rain out water. Although the most intense rain actually scales with that vapor amount.
Okay.
But, sorry.
No, it's okay. So if there's more water vapor in the atmosphere, is it going to feel more humid?
Not necessarily, because, a lot of that is related to, I'm actually not sure I should answer this on Zoom. I might have to email you back because I might screw this up.
Yeah, it's all right. I don't know is a perfectly acceptable answer.
I'm not sure. One thing I will say is that the actual relative humidity, which is sort of the degree of subsaturation. So again, I mentioned that if you take a blob of air at 300 Kelvin and a blob of air at 302 Kelvin, this blob can hold more water vapor. It doesn't necessarily mean it will, because that's sort of an upper bound on what it can hold. The other part of the problem is the relative humidity, which is a little bit built into how humid it feels. For example, a desert is not very humid at all, even though it's very hot.
Okay, so let me see if I got this straight. So, like, basically, the reason things feel humid is because your sweat can't evaporate, right?
Right.
And so even if it's hot and there's a lot of water vapor, if the air can't accept any more, it's going to feel humid. But if it can, it'll feel less humid.
Right. Yeah. And I should probably defer to this question about how humid it should feel in the future. I'm not sure. I know because there's other things built into that question.
Just trying to make this more relatable to people.
Yeah. I hear you. I should probably get back to you on that one though.
Okay. Yeah, that's fine.
For now, I'll say I don't know, but just to finish that thought, that degree. So say those two blobs are both, instead of holding all the vapor that they can, they only hold 80% of the vapor that they can. So that's an 80% relative humidity.
Okay.
So it turns out that the relative humidity doesn't change a whole lot in the future. So that's why you can still say those two blobs, that blob that increased the temperature by 1 or 2 degrees, it still will hold more water vapor in the future because it can, and also because the degree at which it's subsaturated hasn't changed much. So it hasn't met its potential, but it's still, because the potential is larger and it hasn't changed, it's still holding more water vapor.
Okay.
Yeah. But yeah, I can maybe write this down in an email to make it. I tend to be a better writer than I am a speaker.
Yeah,
so.
that's fine.
All right.
So let's get to the big question here, right? So if, with all that being said, if Venus and Mars formed in opposite places, right? Mm-hmm. I guess the first question is, what would Mars look like in that case?
Okay, so Mars in Venus's orbit.
Yeah.
All right. So Mars in Venus's orbit it's a good one to start with, because it's maybe the less interesting or the less different than it is case. Mars in Venus's orbit would probably end up somewhat like Venus is now. It would be very hot. The big difference, one of the big differences that kind of motivated this question, is the planet size. And Mars is smaller than Earth or Venus. And so if we did the swap, Mars to Venus, you still, basically all the issues that arose with the runaway greenhouse, with making it very hot, would still be there. So I think Mars at Venus's orbit would be still a very hot planet. Now, there's just a few things I should mention about how Venus ended up how it did, because it's thought, and again, we don't actually know Venus's history very well, and not just because we haven't been there, but because it's there's no geologic evidence of 4 billion year old Venus terrain.
So is Venus also geologically like inert?
It's not. There is it's probably does not have plate tectonics, but there is evidence of volcanism on Venus. And it has undergone so-called global resurfacing events in the not too distant past. Now that could be several hundred million years ago or something like that. But because of these resurfacing events, you have to look very, very hard to find, evidence of what happened on Venus a long time ago. It's not very well preserved.
So for the most part, like the last resurfacing event is as far back as we can go, essentially.
Essentially, yes, and there might be some certain
patches.
Patches or something. Again, this part of it's not quite in my wheelhouse either, the geology, but but essentially we have no information of Venus going back too far. Mars, on the other, in some sense, Mars, we have more of a glimpse at its past than we do on Earth, because on Earth we also have plate tectonics. We have plate tectonics, not also, but we have plate tectonics. We have, the seafloor is always pretty young because it's being constantly recycled. And so you have to find patches as well on Earth for very old rocks. Whereas on Mars, it's tectonically dead. There's no more liquid water. It's very thin atmosphere. So it's much easier to preserve those ancient environments. But anyway, let me just talk a little bit about the sort of story of Venus.
Sure.
Which and again, we don't actually know if Venus underwent a runaway greenhouse. It's a popular theory because of just the observation that it doesn't have liquid water anymore. It's very hot. The story of how it ended up with a very dense CO2 atmosphere is sort of consistent with a post-runaway greenhouse phase. And there is also, and I can send some information along to you, there is some isotopic evidence with the fact that if you look at the little amount of vapor that is in Venus's atmosphere, it's very enriched in deuterium relative to hydrogen. So we think a lot of the light isotopes escape to space, and people who do that kind of have mapped out that enrichment to mean Venus could have had a global ocean in the distant past when you look at how enriched it is. But there's a lot of speculation in those numbers or those estimates. All right, so the runaway greenhouse essentially occurs, and sorry, I started talking about this, but the runaway greenhouse, it's more than just a positive feedback from water vapor. It's a water vapor feedback that is so strong that essentially the planet cannot lose enough radiation to space such that the absorbed sunlight exceeds that value, right? And so you're sort of in a permanent radiative imbalance in which the planet's receiving more sunlight than it can lose to space, because you're just adding more and more water vapor to the planet or to the atmosphere, and so the greenhouse effect, the positive feedback, is such that the planet's outgoing radiation just can't keep up with what's coming in, and so it just keeps getting hotter. Now, eventually that terminates when there's no more ocean, and actually when the planet's hot enough to start emitting sort of visible light, when water vapor has some windows where it's transparent. So you can start to lose energy now in like visible light, but that's after it's 1400 Kelvin or so. So that's what the runaway greenhouse phase means. There's been some discussion in both popular media, I guess, and also in the scientific literature about whether Earth could ever have a runaway greenhouse now. It can in the future, certainly when the sun gets brighter. And that's something in your last video you talked a little bit about, in a billion years or so, Earth might lose an ocean, and it may enter a runaway greenhouse phase. But right now, Earth probably can't have a runaway greenhouse because I mentioned that the absorbed sunlight has to exceed this radiation limit of a moist atmosphere. It turns out that the absorbed sunlight is under what that limit is. And so even if you burned all the fossil fuels on the planet, you could end up with a very hot planet. You can end up with an uninhabitable planet, but not a true runaway greenhouse.
Okay.
But that's not true in the future. With Venus, the conventional thinking is that it's a little bit closer enough to the sun such that, and this would be true on Mars if you swapped Mars for Venus as well, that it received enough sunlight so that absorbed sunlight was higher than that moist greenhouse threshold. And so you could trigger a runaway greenhouse. That's not the only solution to the problem. There are intermediate cases. There are cases where the upper atmosphere is moist. It's very moist, but it's not in a runaway greenhouse. But then you end up losing hydrogen through atmospheric escape processes, so that you're sort of in people call it a moist greenhouse, which isn't quite a runaway greenhouse, but it's sort of an intermediate between what we have on Earth and what a runaway greenhouse is. So it's like a habitable planet, but it's losing water to space, and so you can sort of lose an ocean worth of water over time. So there's still, I guess, openness as to whether a true runaway greenhouse occurred on Venus, but it is something that's possible.
So it's possible, I guess likely, that Venus didn't start with a runaway greenhouse already happening. Like it lost some, like it lost some gases to space, and as a result, the atmospheric composition changed and it switched the absorption and emission balance.
Right. So actually, there was a paper by one of my kind of colleagues. It was titled "Was Venus the First Habitable Planet?" And the argument was actually that Venus and Earth started very similarly, and Venus could very well have had an ocean, 4 billion years ago, and the sun was fainter. This is something that props up in planetary comparative climatology a lot, is the fact that for all the planets, you have to deal with the fact that the sun was, about 70% its current brightness during formation, during 4.5 billion years ago. It kind of just an offshoot of your last video that the sun gets brighter over time because of fusion and core contraction and the increase in the core temperature that's required to maintain its weight. But when you do that backwards, it's about 70% the current luminosity 4 billion years ago. So for Earth, that's been a problem. It's called it was called the faint young sun problem. I'm sure you've heard of that. Carl Sagan came up, I think, with the term. It's kind of not a paradox now for Earth. It still is for Mars. It's not to say we can completely solve it, just because in some case it's not a there's just some irreducible uncertainties,
Right. But that the faint young sun paradox is more of it's more complicated for Earth, because even though the sun was dimmer and cooler, like the atmosphere might have been able to retain more heat or something.
Well, yeah. So it's not as complicated for Earth as it is for Mars, because for Earth you can easily get above freezing. So the whole paradox arises is that if you just take a climate model and you give it, you have it so that you kind of have a present day Earth climate with the present day amount of sunlight, and then you abruptly dial down the sunlight to 75% its current value, then Earth freezes over. But you can increase the greenhouse effect to sufficient values with CO2 to get around that. It's just kind of a question on what gases did that, and I won't say there's no constraints. There are a lot of constraints on what you can do with chemistry. There are constraints a little bit in the geologic record, but for the most part, the faint young sun problem, it's more of I don't think anybody really sees it as a problem anymore, as much as just trying to find the exact cocktail of chemical, geochemical consistency to give you, that greenhouse effect. But it's certainly true that you can have that greenhouse effect give you above average temperatures for above freezing temperatures. For Mars, it's a lot more complicated, because there's also evidence of liquid water in Mars's distant past. There's valleys and networks and all kinds of fluvial features in Mars. But to get the right atmosphere is very challenging. So there's been other mechanisms proposed in the last few years involving hydrogen as a greenhouse gas and so on. But it's a tougher problem on Mars. But for Venus, or Mars and Venus's orbit, either way, it means there's no paradox, but it could be very well that the planet formed at sort of temperate temperatures after after the sort of bombardment phase, and when things settled down a bit, that you did have a liquid ocean on Venus. And presumably that'd be true on Mars and Venus's orbit as well. You could have a period of very Earth-like temperatures. Eventually, as the sun gets brighter, the classical argument has been that at some point this sort of runaway, limit, that limit that I mentioned of, and there's a name to that limit as well. It's depending on who you want to credit to as having discovered it. Some people call it the Kobayashi-Ingersoll limit. Some people call it the Nakajima-Simpson limit. I could send you some stuff if you get into this, but essentially that threshold amount of sunlight that the planet absorbs exceeds what the planet can lose in infrared radiation. At some point, the classical argument is that Venus found that transition and then it went runaway.
And so that would happen with Mars at Venus's orbit, even with the thin atmosphere?
It would So it would happen. Actually, it would be even easier on Mars because the runaway greenhouse threshold depends a little bit on the planet radius or gravity, and it's a little bit easier to run away with a smaller planet. But that's not it's not a huge term, but it would be a little bit easier to run away on Mars than on Venus. But the thinness of the atmosphere is not what matters. What matters is whether it had an ocean to provide this source of water vapor feedback. Because even if you don't have really anything else in the atmosphere, a planet that if you still had an ocean that was capable of being evaporated into the atmosphere, then you would have a runaway greenhouse. And so the runaway greenhouse story it's essentially exclusively a story of water vapor. It doesn't much matter what else is happening in the atmosphere. So Mars would definitely run away in Venus's orbit. Now, if you don't have an ocean to begin with, if you just have a land planet, then it doesn't really make a lot of sense to call it a runaway greenhouse for that reason. But it would just be a lifeless hot rock that baked. And now the other so then the question of the post-runaway greenhouse phase, which I think touches on your question of the atmosphere, because a lot of people confuse the modern day 90 atmosphere pressure of CO2. Some people confuse that with the runaway greenhouse effect. It's really a post-runaway greenhouse phase. Again, if you start off with a very thin atmosphere or an Earth-like atmosphere, it doesn't really matter. You'll get a runaway greenhouse just with water vapor going on. So the aftermath of that, though, when you have no more liquid water, that's sort of the end state of a runaway greenhouse. When you have no more oceans and you have no more liquid water. So now the question is, how did Venus acquire a 90 bar CO2 atmosphere after that? And a lot of the traditional thinking of that is that essentially what happened is you lost the ability to weather rocks, and that's a big sort of, I would say, stabilizer of Earth's climate, is when you have Earth's sort of long-term carbon cycle is a balance between volcanic outgassing of carbon and weathering of rocks through rainwater and the minerals that they deliver to the ocean, and some of that gets abducted into the seafloor. That essentially is a long-term. It's actually a negative feedback. It's one of the reasons why Earth's climate, if you look back geologically, there's a lot of fluctuations, but it's not, it hasn't gone Venus and then Mars, and it's relatively small amplitude. And a lot of that people think is because of this weathering feedback, the fact that weathering depends on the climate. And you get more weathering in a hot climate and so you draw down CO2 a little bit more in a hot climate. Whereas if you make the Earth a snowball, for example, and this probably happened in Earth's past, it's a very cold climate. And so it's very cold. There's not much weathering. And so the volcanic outgassing is still going on in the background. You're still building up CO2. And eventually you can build up enough CO2 to deglaciate. And then weathering can start happening again. But once you lose liquid water, as occurred on Venus at some point, then you no longer have a weathering mechanism, and so carbon is basically free to just stay in the atmosphere, and actually there's probably similar amounts of carbon on Venus and Earth. It's just that on Venus it's all in the atmosphere, and on Earth it's all in rocks essentially. But if Earth didn't have a mechanism to keep the carbon in the rocks, then the only other place is to have an atmosphere of all CO2, essentially.
Okay.
So that's what we think happened. So I guess the one thing worth mentioning is that the CO2 enriched atmosphere of Venus is a post-runaway phenomena that occurred because you don't have liquid water anymore. It's not itself a runaway greenhouse. It's just a strong greenhouse effect.
Okay.
Yeah.
And so if Mars used to have water on it and it formed in Venus's orbit, we would expect a similar thing to happen. We'd expect the runaway greenhouse effect to happen for a period, and then the carbon dioxide would build up after that.
Right.
Okay.
Yeah. So in a sense, so I guess it was a very long explanation of different things going on, but I think the conclusion is that essentially Mars would be very much like Venus is now, and in fact, even easier. So probably because as I mentioned, the runaway greenhouse threshold is a little bit lower on a small planet. And so Mars would run away a little bit easier. And also any atmospheric escape that happened would be a little bit easier on Mars too, because it's a smaller planet. The gravity's not as strong to keep some of that stuff, gravitationally bound to the planet.
And so in a sense, it wouldn't be the atmosphere wouldn't be as thick as Venus, probably.
So it's so that's a good question. So Mars probably, depending on how much carbon it had. CO2 is pretty heavy. So you don't necessarily, even with Mars, you don't necessarily lose a lot of carbon dioxide. But what little atmosphere Mars has now, in fact, is pretty much all carbon dioxide. But so I think you could still develop a reasonably robust CO2 atmosphere on Mars in the aftermath of the runaway greenhouse. But it's a good question. I don't know. I don't think anybody knows what would the pressure of CO2 be on Mars and Venus's orbit right now. I can't give a number to that, but I would expect you would still have a relatively thick CO2 atmosphere now on Mars.
All right. So last question, and I'll let you go here. Right. The last question is, what would happen if Venus formed at Mars's orbit?
Yeah. Okay. So this is probably, in a sense, the most interesting difference from what the observed state. So the big difference in the evolution of the two planets is going to come in through the size of the planet. Now, the story on Mars is essentially that it lost its atmosphere through atmospheric escape, because it's a small planet. It doesn't have the gravity to sort of keep a very thick atmosphere for an extended period of time. And if some asteroid comes along and hits the planet, you could strip away parts of the atmosphere at different times. So Mars, essentially, it's kind of a depressing story of a planet that just, probably had a thicker atmosphere in the past and just couldn't hold on to it because it was too small. But again, probably had a thicker atmosphere in the past, and probably was warm enough, even with the fainter sun in the past, and with the more distant orbit to the sun. Even with those two things, it probably had liquid water in the past at some point. But with Venus at Mars's orbit, you no longer really are constrained by the size of the planet, and so. So if you no longer have atmospheric escape as a big limitation, then we can it's essentially a similar problem as if Earth was, if Earth was at Mars's orbit, they're pretty much the same problems. Assuming, and again, I don't know, the plate tectonics
right.
is sort of a complex variable in this story that it's kind of the wet towel when you're doing this thought experiment, because plate tectonics can take on a very different form depending on what kind of planet you end up forming, what kind of history it went through, how much water ended up in the mantle, and just all these things. Some people tell me it's sort of chaotic in the sense that, even Earth could have had different plate tectonics if it did something different early in its history. And so, but that matters for the recycling of things from the surface to the atmosphere. So anyway, if we kind of ignore that problem, if you have Venus or Earth that is in Mars's orbit and you allowed it to form in that way, then this weathering mechanism, assuming you have sort of outgassing, volcanism, plate tectonics, if you have a geologically active planet, then this weathering mechanism I mentioned should be operating, and it's sort of operating in the direction of having a little bit more CO2 in the atmosphere, because it's a colder planet. It's not weathering as efficiently. And so essentially the low sunlight is sort of balanced by low weathering, keeping a relatively thick CO2 atmosphere. And so the conventional, when you're talking about the habitable zone boundaries, which is a thing that has been of a lot of scientific interest over the decades, is what is it, the inner edge of the habitable zone when it's too hot for liquid water, and the outer edge of the habitable zone when it's too cold for liquid water to form. The inner edge has always been defined by the runaway greenhouse kind of limit that I mentioned before. The outer edge it's pretty tricky, because in principle you can always accumulate greenhouse gases to keep your planet warm. So the conventional definition was just, if you just look at carbon dioxide and ask the question, well, what if you kept moving a planet further and further from the star, what would happen? And eventually, essentially the CO2 in the atmosphere increases with orbital distance because of this weathering mechanism that is supposed to operate. Again, it's hard to verify this. So, but eventually it just gets. Eventually, you get to the point where essentially the outer edge of the habitable zone is defined based on when CO2 can no longer warm the planet anymore. And that can happen. Eventually, CO2 actually becomes a good Rayleigh scatterer. So that Rayleigh scattering offsets the greenhouse effect. So that's one limitation. And eventually CO2 just builds up. When you're talking about not Venus temperatures, if you're just talking about Earth-like temperatures, eventually CO2 buildup is going to lead it to condense. And so eventually you just can't build up CO2 anymore. And so that sort of has been the defining point of the outer edge of the habitable zone. But But if Venus formed in, or if you put Venus in Mars's orbit and let it evolve, what probably should happen is that it could be a habitable planet. It could be Earth 2.0. It's just kept temperate by less sunlight and more CO2 in the atmosphere. And so it's, depending on other details, which are complex, it could very much be habitable. And just, maybe it would, maybe it would go through periods of snowball transitions or something like that. It would be maybe more prone to, global freeze-overs that aren't very friendly for life. But it could very well just be an Earth temperature planet that is just kept Earth temperature by a higher greenhouse effect and less sunlight. But if that weathering mechanism persisted over geologic time, then it seems like you could very much keep it habitable.
That's a really interesting thought, though. So like we don't know for sure whether or not it would be habitable, but it's definitely possible.
Right. Yeah.
Given several other, bits of information.
Yeah. That's something. I think that's true. And that was, I guess, one of the outcomes of this conference talk that, emerged from this discussion was you could probably have Earth and Venus at Mars's orbit as modern day habitable planets, if that's how things worked out.
But they didn't, unfortunately.
Yeah, they didn't. But that'd be interesting. Yeah. So.
All right. Well, I guess. Thank you so much for your time today. I know we went a little over an hour here, but I've learned a lot. This was very informative.
Yeah, I have a tendency to ramble on, as you've probably inferred. Because these are kind of complex problems, and anytime you dig into a subject, there's like 10 other things that. I'm like, I have to mention this, but if you follow up with this question in a video or whatever, I can send some material to you, and I'm wide open on email to follow up.
That would be great, because if I have sources, I can include them in the video description for people to read if they want to.
Sure.
I've got at least a video or two to do before this, but I definitely want to turn this into a video. I'm very excited about it.
Okay. It's not great.
I just can't make any like immediate promises about when it's going to come out, but it will come out.
Of course. Yeah. That's great.
And of course, I'll run it by you when it's finished, so that like you can be like, well, you probably shouldn't have said that there or whatever. And,
sure. Is it once you actually make a video and you've done your whole thing, is it pretty easy for you to go back and like remove or add sentences or?
Yeah, I can tweak it if I need to. I've made videos before where I'll get finished with it and then I'll watch it and then I'll think it's fine, but then I'll run it past somebody else and they'll be like, that was a little, like, you need just a little bit more explanation there, and I can just splice it in. And
yeah.
Especially if it's just like an animation in my voiceover, like that's really easy to add in if I need to, or so it's totally adjustable. It's what's most important to me is that it's accurate.
Right. Yeah.
And I'm definitely not an expert on this, so.
I'm pretty. I'm like, that detail's wrong, and sometimes it gets me in trouble because it's like 99% right, but I'm like, but that one word is wrong. So
right. I made a video about terraforming Mars several years ago.
Yeah.
And I wasn't as nuanced as I should have been, and people like took me to, just really went at me in the comments about it. And so
okay. I haven't seen that one, but all right.
There are some things that I meant to say something slightly different and I didn't. And then like it comes across as this like blanket statement when it shouldn't be. And so there's issues there, but.
Yeah. Okay. Yeah. Well, I'll definitely, yeah, I can send some literature and then I'll try to think of good documents that are probably something like review papers or something that tend to be less technical, but more also rigorous, and or like a book chapter or something. I can think of a few things that I can send over. And then, yeah, I'll be wide open on email, or if you want to Zoom again in a few weeks, I'll be happy to do that. So
sure.
Yeah.
But again, Chris, thank you for your time, and I'm sure we'll be in touch by email.
Okay.
For
Great.
something, but yeah, if you can send me stuff, that would be great. And I guess have a good rest of your day.
Yeah, you too. Yep. Thanks for doing this.
Yep.
Bye.
Bye.